everyone, it's Veronica. So today I'm going to be presenting on pediatric vulnerability to radiation. So from this presentation, we will be able to understand the difference between non-ionizing and ionizing radiation and be able to give examples of each. We're going to identify the types of sources of radiation exposure ranging from natural to human-made. We're going to understand the biological and developmental factors that contribute to pediatrics' increased vulnerability to radiation. We're going to understand the acute effects and long-term risks of radiation exposure to pediatric patients. And lastly, we're going to explore radiation-reducing strategies, including dose optimization techniques and alternative imaging modalities. So starting off with types of radiation exposure, we have two types. Non-ionizing radiation is radiation that does not have enough energy to remove electrons from an atom. And examples of this include radio frequency, visible light, microwaves, infrared radiation, and ultraviolet light. And then ionizing radiation is radiation that has enough energy to remove electrons from an atom, creating ions. And examples of this include X-rays, gamma rays, alpha particles, and beta particles. So next we have sources of radiation exposure. So under natural, we have terrestrial radiation, which comes from the crust of the Earth, cosmic radiation from the sun and beyond the solar system, and internal radiation, which is radionuclides. And then for human-made, we have consumer products that contain radioactive materials, nuclear fuel, atmospheric fallout from nuclear weapon testing, nuclear power plant accidents, and medical radiation. And then I have a table here that shows medical radiation exposure from the year of 2016, and this is actually in our Rad Bio book. So I have all of the modalities listed, and then it looks like the highest percentage of radiation comes from radiography and fluoroscopy, then CT, then nuke med, and then lastly interventional. So next, going into the biological effects of radiation, we have indirect effect and direct effect. For indirect, if a cell is exposed to radiation, the probability of the radiation interacting with the DNA molecule is very small, since these critical components make up such a small part of the cell. Each cell is mostly composed of water, usually 70 to 80%, so as a result, radiation has a better chance of interacting with this water. And then when the radiation does interact with the water, it can break the bonds that hold the water molecule together, producing fragments such as hydrogen and hydroxyls. These fragments can recombine or may interact with other fragments or ions to form compounds that are harmless, like water once again. However, they can combine to form toxic substances such as hydrogen peroxide, which can actually cause cell damage. And then for direct effect, this occurs when radiation interacts with the atoms of the DNA molecule directly or some other cellular components that are necessary for the cell to reproduce and survive. If enough atoms are altered to inhibit proper chromosome replication, or if the information carried by the DNA molecule is greatly altered, the cell may be destroyed through this direct interference with its system. So cells have long double helical DNA molecules that contain the instructions needed for an organism to develop, survive, and reproduce. DNA damage means altered nucleotide sequence, which leads to the expression of dysfunctional proteins, which in turn impacts cells' genetic code in a negative way. The DNA damage response pathway responds to cellular damage using signal sensors, transducers, and effectors, but the repair rate does vary according to cell type and age. A cell with a damaged ability to repair DNA can either enter a dormant state, undergo programmed cell death, or undergo unregulated cell division. Since ionizing radiation does damage the DNA, which is crucial in cell reproduction, it has its greatest impact on cells that rapidly multiply. So next I have a chart here that shows difference in radiosensitivity by age. So when looking at the numbers, you can see that the committed effective dose coefficient are larger for children than those for adults. So radiosensitivity numbers are higher for children, and the younger that they are, the higher the sensitivity, but this can also depend on gender. So now for pediatric radiation vulnerability, starting off with body composition. Children are more vulnerable to radiation doses due to their smaller body size and organ size, along with other factors. Their bodies are made up of more water and less fat than adults, and as we know, water molecules are a primary target for radiation interactions. And then their organs are closer together, leading to greater radiation exposure across multiple tissues, and their organs are still growing and maturing, which also makes them more sensitive. And then an infant's body shape is shorter and wider than that of an adult, so when the trunk of a child's body is x-rayed, a larger part of their body is within the radiation field, which is then more affected by scattered radiation. And then I found that there are differences in the location of at-risk tissues such as hematopoietic bone marrow between adults and children. So in adults, 74% is located in the skeleton of the trunk, 9% in extremities, and 8% in cranial bones. In infants, 29% is located in the skeleton of the trunk, 35% in extremities, and 27% in cranial bones. So this means that infants have larger proportions of this at-risk tissue in all parts of their body. So next we have rapid cell growth and division. Children's cells divide and multiply at a faster rate than those of adults, so this increased rate of cell division opens up more opportunities for radiation to interrupt the process and cause cell damage. Then for prolonged biological half-life, unlike adults who only need to maintain their bodies, children require more nutrients than they excrete in order to grow and develop. So because of this increased consumption, radioactive isotopes remain in their systems longer, lengthening their biological half-life. And the longer that these isotopes remain in their bodies, the more likely they are to cause cell damage. For underdeveloped DNA repair mechanisms, we have repair systems that our organisms use to identify and remove defective cells, and these systems are not yet functional in children, especially prenatal children, which makes them more susceptible to radiation damage. And then for cumulative exposure, malignancies have a long latency period, so in conditions caused by radiation, decades can pass between the initial exposure and the first identifiable sign of illness. So unlike older individuals, children have many years to live ahead of them, so this means that they may be unfortunate enough to experience the end of this latency phase. So next we have effects of radiation exposure to pediatric patients. Some short-term effects include acute radiation syndrome, nausea and vomiting, fatigue, hair loss, and skin reactions. And for long-term effects, we have increased cancer risk, genetic mutations, organ damage, cataracts, and growth or developmental delays. So next, going into radiation-reducing strategies for pediatric patients, we can first follow the ALAR principle, which eliminates doses that have no direct benefit to the patient or image quality. We can adjust equipment to pediatric settings so we can tailor exams to the size and age of the pediatric patient. We can use digital X-ray detectors and X-ray beam filtration to reduce dose. We can increase collimation of images as much as possible without clipping important anatomy, so we can reduce primary and scattered radiation. We can shield by using lead shielding such as lead aprons, thyroid collars, and gonadal shields, which can be used to protect sensitive areas from radiation. And lastly, we can use alternative imaging modalities that don't use ionizing radiation, including ultrasound and MRI. Lastly, I just want to go over some case studies and research findings. So for the Chernobyl nuclear disaster, I found that children and teens living near the plant at the time of the accident were more likely to develop thyroid cancer as a result of their exposure to radioactive iodine, and this higher risk was not observed in the area's adult population. I also found that those who were exposed to high radiation levels before the age of 5 are more likely to suffer health repercussions later on. For the Fukushima nuclear accident, I found a report that was released in 2013, and it concluded that individuals exposed as adults were not expected to develop thyroid cancer above the background level. However, there was some increase expected for infants and children. And according to the Fukushima Health Management Survey, it found that 36% of 38,000 examined children developed thyroid cysts or nodules, and these don't necessarily indicate malignancy. However, they do highlight the importance of monitoring potentially at-risk people. And then in 2001, a study calculated the chances of radiation-induced deadly cancer from CT scans of children. It was found that CT scans of these children resulted in a 10-fold increase in estimated risk when compared to CT scans of adults, with projected risks for abdominal CT exams much higher than those of CT head scans. So to conclude, in this presentation we went over the difference between non-ionizing and ionizing radiation and gave examples of each. We identified the types of sources of radiation exposure ranging from natural to human-made. We went over the biological and developmental factors that contribute to pediatrics' increased vulnerability to radiation. We listed the acute effects and long-term risks of radiation exposure to pediatric patients. And lastly, we explored radiation-reducing strategies, including dose optimization techniques and alternative imaging modalities. And then here are my references. Thank you.